everybody was doing it. It's good. Me and Baker. Winter. Yeah, he was doing it in the fall. Kind of laid back. But just because I said that, don't diminish how the other people will do. They'll be good too.
Monica said she took your class because
I had a number of that happen. Nothing more radical. And it's not instructor. You know, it's got creativity, whether it's project. Place where it does that way. Well, that's my truthful that those who really have bad experience with better education, great experience with each other. It grew.
That? Not that way. So I'm going to write that out.
Well, you hit black. Okay.
B is black.
I thought I
W
hit
is
a
white.
black.
You hit any key.
Okay, go ahead.
So excuse me, everyone. Hello. Excuse me, if I could have your attention, please. Thank you. The microphone, maybe I can't tell if the microphone's working, so I'll just shout. So welcome, everyone. My name's Joe Helbley. I'm the Dean of the Thayer School of Engineering, and it's my pleasure to welcome you to today's special edition of our weekly Jones Seminar. Today we'll be hearing from Professor Bill Lotko, the inaugural holder of the Sue and John Ballard Professorship. Before I invite Bill up to the podium and ask him to speak, however, I'd like to do a few things. First, I'd like to recognize, with special thanks, John Ballard, Dartmouth class of 1955, Tuck Thayer, 1956, and his wife, Sue, who unfortunately cannot be with us today. John served as a Thayer School overseer since 1989 and was its chair from 1998 to 2007. He was a 1988 recipient of the Sylvanus Thayer Fellow Award, and in 1998 was awarded the Robert Fletcher Award. With John today is his daughter Cynthia Kittleson, her husband Doug, and their daughter Kelsey, Dartmouth class of 2017. And it's through the generosity of John and Sue Ballard that we're able to inaugurate this professorship and celebrate the work of Professor William Lotko. So please join me in thanking John and Sue. John and Sue Ballard established the Ballard Professorship to recognize and reward members of the Thayer School faculty whose teaching is true to the highest standards of Thayer's educational mission and whose scholarship has contributed significantly to the advancement of interdisciplinary knowledge. The inaugural holder of the Ballard Professorship, William Lotko, joined the Thayer School faculty in 1984, becoming a full professor in 1995. You've been here longer than I realized. He directed Thayer's MS-PhD programs from 1996 to 1999, and then served as Senior Associate Dean from 1999 until 2004, when he agreed to serve for a year as Interim Dean. Bill has a Bachelor of Science degree in Engineering Physics from the University of Kansas, an MS in Condensed Matter Physics from the University of Missouri, and a PhD in Plasma Physics from UCLA, nicely demonstrating the interdisciplinarity of Dartmouth and the Thayer School of Engineering. Bill's research focuses on systems-level studies of the solar-wind magnetosphere-ionosphere interaction with applications to space weather prediction, which he'll tell us a bit about shortly. He has done scientific work with Los Alamos National Laboratory, the Space Sciences Laboratory of UC Berkeley, the Max Planck Institute in Munich, and the National Center for Atmospheric Research, or NCAR, in Boulder, Colorado. Bill is a founding member of the Center for Integrated Space Weather Modeling and NSF Science and Technology Center, a research affiliate of NCAR, former editor-in-chief of the Journal of Atmospheric and Solar Terrestrial Physics, and a fellow of the American Geophysical Union. Bill teaches courses in engineering design, applied mathematics, electromagnetic fields and waves, magnetohydrodynamics and plasma physics, space systems engineering, and on issues in technology and society. Bill has been a valued member of the Thayer faculty for, as you heard, nearly 30 years, and he's also been a valued colleague throughout my tenure as dean. Bill was interim dean in the year before I arrived, and he was instrumental in helping me come to know this place, understand the institution, and the incredible contributions that our faculty and staff make to our students in their education. So I am profoundly pleased and honored to be able to introduce Bill as the inaugural holder of the John and Sue Ballard Professorship. Bill?
I just asked Joe to give John my lecture notes, so, just in case. Many quizzes. Okay, thank you for that introduction. It reminded me a little bit about half a dozen years or so ago when I was elected to the Phi Beta Kappa Society by one of my colleagues here, and I was standing up on the stage in Spalding, and they read through this long list of all of these things, and I looked out at the students and I said, look at all the stuff I had to do to get here, and you're here today, 4 years. But thank you for that introduction, and thank you, John and Sue, for making this lecture possible. It's one of the delights is to be invited to talk about your work, and I view this as an opportunity to do that, and I hope I can share with you some of the excitement I have for the kind of research that I do here, and my students and research scientists and colleagues who work in this area. I actually had developed a whole set of slides, and I went to the Alan Alda lecture yesterday on communicating science and decided I had to tear them all up and start over this morning. I wasn't lying, Joe. Okay. Forecasting space weather. I'm going to talk about some of the things that we do here at Dartmouth to enable space weather forecasting. We're not meteorologists. We don't forecast, but we work with our colleagues who do forecast space weather. And we're on a trajectory, I think, to implement numerical weather forecasting models like the kind that are used to forecast the weather here in the troposphere. That's the main method for developing forecasts that go out days, is to use numerical forecast models, and that's our contribution here at Dartmouth. A number of people have asked me what this image is, so let me just start. I think without writing on there, hopefully you can see some of the geography on the map. See the Great Lakes there. So this is an image taken by a satellite that's operated by NOAA that was launched by NASA in partnership with JAXA, which is the Japanese Space Agency. It's actually a weather satellite, but on some occasions, when the light is bright enough at night, it can image aurora. And what you're seeing here is aurora over most of Ontario. It's a consequence of a relatively moderate, weak, minor to moderate storm, geomagnetic storm, and I'll talk a little bit more about that as we go along here, that occurred on, I think this particular image was taken on October 8th, 2012, just about a year ago. Gives you an idea of the dynamics and the scale of the phenomena that we're talking about in space weather. Okay, I hope as we go through this lecture that I will be able to answer some basic questions for you. What is space weather? What causes it? How does it affect us? Can it be forecast? How can forecast be used? I mean, it's one thing to forecast. If nobody cares, what does it matter? I love this slide. I discovered this figure from one of my wife's former PhD students who put it in his thesis. In case you can't read the date on this slide, 1872. Space weather has an incredibly long history at Dartmouth and the Thayer School of Engineering. And I know Monday I'm going to hear from Joe. Bill, it's been done for 140 years. Isn't it time that we stop this kind of stuff?
Not if you can still get it funded.
Okay. So, actually, I want to mention one thing. John Sloan Dickey, started the Great Issues course at Dartmouth, and he had a definition for what a great issue is. It had to have three elements. It had to have historical depth, it had to have a moral or ethical dilemma, and it had to have significant current interest. Now, I'm not going to hit all three of those today, but I will hit two of them, and if we ever send humans to Mars, we'll probably be dealing with all three of those issues. Okay, so the historical depth. Probably most people here don't know anything about Elihu Quimby. He was instrumental in starting the Thayer School. He was the inside professor at Dartmouth before there was a Thayer School, who worked with the faculty and the president, Thayer, and Bobby Fletcher to make sure that there was a Thayer School that could come here. And one of the issues they were concerned with in the early days, in the 1868s, was whether the students who would be admitted to the Thayer School of Engineering could pass muster in mathematics. That was going to be a criteria. It's amazing how some things never change. Okay, so why would a professor of mathematics and civil engineering be interested in magnetic storms in 1872? This is the test part. Surveying. How did they do surveys in 1872? The magnetic needle. Okay, that's exactly the answer. And so this little document that's available over in Baker Library basically it chastises the surveyors at the time about using the magnetic needle without caution because of this effect here. These huge fluctuations in the magnetic field at the surface of the Earth completely can give completely erroneous results on a survey. Okay, I'm going to give you a sense of space weather, but I want to show you an animation developed by NASA, which actually tells a lot of the story. You see the sun ejecting ionized gas. In this case, it heads earthward. Earth has a magnetic field surrounding it due to the geomagnetic field at the Earth. There's a conversion of gas dynamic energy, kinetic energy of the flow coming to Earth, into electromagnetic energy, and then ultimately back into particles, which gets dumped into the auroral zone, the high latitude region that produces the auroral lights. So in one sense, this is not complicated. The sun explodes. When an explosion happens, mass goes out. This happens to be ionized mass. And because it's ionized, when it sees the Earth's magnetic field, it interacts through the Lorentz force. And so it compresses the magnetic field of the Earth. And the intricacies happen with that interaction of the magnetic field. And there are some subtleties there, and a lot of the current research is involved in trying to understand what's going on there. Now, I'm going to say a little bit about climatology of weather. You kind of need to say something about that. It doesn't snow in July typically in the northern hemisphere, and that has something to do with climatology. But the weather is, when does it snow or rain? And in space weather, the climatology to a large extent is driven by the solar cycle. And the solar cycle is 11 years approximately. It's not exactly 11 years long. But in this diagram here, you can see that at solar minimum, 1996, the sun's relatively, it doesn't have a lot of bright spots or sunspots in it. And then when you come to solar maximum, in this case around 2001, it's really lit up. And then it cycles back around to solar minimum, and then that process starts over again. And so right now we're right near solar maximum today. It's not clear exactly. You won't know when it is until you're in the declining phase of solar maximum. Okay, so I need to introduce a little bit of jargon here. This is the Ellen Alda part, so that people are with me, because I'm going to use some of these words, and you may not, if I don't explain them now, I may lose you along the way. So the solar wind is that ionized gas. It's there all the time. It's just that during these explosions on the sun, it's very much enhanced. The densities are higher, the speeds are higher. It can be moving it up to 1,000 or more kilometers per second, not per hour, but per second. This is an incredibly fast wind. In fact, on an airplane, you're going at Mach less than 1, typically, and 600 miles an hour or something like that. Compare that with the speeds in the solar wind, which, based on the local wave speeds in the solar wind's moving at Mach 4 to 10 or more sometimes. It is a very fast stream. And as a consequence, if a Navy pilot, like John once was, is going at greater than Mach 1, there's a sound wave or a shock wave set up around that object moving through the atmosphere. In this case, the object is Earth, and its geomagnetic field surrounding it, its cocoon, and it's stationary, but the wind is moving supersonic, so a big shock wave is set up in front of the Earth. That's the Earth's bow shock. The ionized gas in the interplanetary medium, or the solar wind, carries an interplanetary magnetic field, and that interplanetary magnetic field has a lot to do with the dynamics that we see in geospace. And I've tried to draw here the direction of the lines. So I'm going to talk about geomagnetic activity, and there are some proxies for that. I'd just like you to understand a little bit about that. So if the Earth were a pure dipole, and if you go far enough away from the non-dipole moments, it behaves like a dipole. And so the dipole, the magnetic field emerges from the southern hemisphere, goes around and comes back into the northern hemisphere. And that's true for all of these so-called closed field lines that you see here, south and north. Now, this so-called ring current is present almost all the time, but during storms, it gets pumped up. This is an electrical current that flows. If you look down on the North Pole, it's flowing in a clockwise direction around Earth, out to distances of 6-7 Earth radii. So the fiducial unit in this business is Earth radius, which is about 6,400 kilometers or so. That's one Earth radius. So there's this current that circulates in this region here on the backside out of the plane, and then circulates around and into the plane, and then it just goes around and around like that. Okay, so those of you who can remember your freshman physics, electricity and magnetism, will know that if you have a current that circulates like this, you use your right hand, all right, curl your fingers, then you will get a magnetic field induced by this current in space, by this ionized gas sitting in space, which it's a conducting gas, will induce a magnetic field like that. And notice that it opposes the direction of the Earth's magnetic field on the earthward side. And in fact, on the surface of the Earth, it opposes the direction of Earth's magnetic field. So when there's a lot of activity in space, and that ring current gets pumped up, the surface field at Earth is reduced. And that's used as a proxy, a remote proxy for what's happening in space. Okay, a little bit more historical perspective here. This is a great diagram going back to when sunspots were first started being recorded. When were sunspots first started? When did they first start to be recorded? Who? Galileo, indeed, right. So we really didn't know about sunspots until Galileo. And we didn't know about magnetic storms until von Humboldt. He was a German. He was kind of an adventurer, explorer, scientist. He was sitting in his laboratory in Berlin and started measuring these deflections on the compass needle. And that was before there was a lot of other electromagnetic activity in Berlin, which would be hopeless today. But back in those days, he could do it. And he was really curious about, what's going on? Why is this happening? And because he was an adventure explorer, he started taking measurements all over the world, well, at least the part that he traveled to. And he realized that this was not a local phenomenon. This is happening globally, everywhere, because of those currents that are circulating in geospace around the Earth. So von Humboldt discovers magnetic storms around the turn of the century in the 1800s. In 1859, this major event, which has captured a lot of people's imagination today and continues to capture people's imagination, it's now called the Carrington event, and I think there's even a television series now called the Carrington event, which pivots off of this idea. But the Carrington event, so the red lines here are on this axis here, and this is a measure. You don't have to think about it very hard. Just think that larger means more ring current, more disturbance in geospace, and therefore more disturbance on the surface of the Earth where they measure magnetic fields. And in 1859, an incredible event occurred. In fact, this event was so large in North America and Europe, telegraph failed everywhere. Some caught on fire because of the induced currents in the telegraph. Of course, they didn't really know what was going on at that time. But Carrington was really, he was a solar scientist, and he observed the sun, and he made this correlation between aurora, solar activity, and what was happening at the surface of the Earth. And so that was when magnetic storms first started to get connected to the sun. People knew about sunspots before then. They knew about storms, but they didn't know they were related. 1872, Quimby records this geomagnetic storm in Hanover. Okay? It sits on this chart. It's amazing. It's not surprising that he saw that thing. And then these are the extreme storms that have been observed, that have been determined, that are over 400 nanotesla disturbance at the surface of the Earth. So you see these extreme storms are not very prevalent, but it turns out they have significant impacts. In 1989, I was sitting, my wife was traveling. About 11 o'clock at night, I get a call from Tai Fan, one of Professor Bank Sunderup's more famous students. He was a PhD here at the time. Calls me up at home. He says, "Bill, you have to go outside and look at the aurora. It's just incredible." We're out on the golf course, or we were out on the golf course. And so I did, and indeed, the aurora was as dynamic and bright as I have ever seen it. And it turns out that in 1989, March 1989, it's a famous storm event, Hydro-Quebec failed. And what happened was that the induced currents that were flowing in the transmission lines at northern latitudes there destroyed some of the transformers at James Bay. And so Quebec was basically without power. It was dark for 24 hours due to that until they could get another transformer in place to fix it. And then I'll talk a little bit about this interesting event, and massive CME misses Earth, and how do we know it missed Earth? And so I'll talk a little bit more about that one as we go along here. Well, okay, let's back off of the extreme events and get a sense of what other kinds of activity. So it turns out, so these are intense storms now, rather than being greater than or more negative than minus 400 nanotesla. These are storms that are less than minus 200 nanotesla. Quite a few more in the space age alone here from 1960 onward. And one of the things that we notice about the climatology here is that these intense storms tend to occur near solar max and in the declining phase of solar max on the way to minimum. They tend to be clustered around there. That's due to solar processes that are occurring primarily. And then going to an even different measure and more events, and KP is another geomagnetic activity index. So you set up a bunch of magnetometers around the Earth, and you measure the geomagnetic deflections on those magnetometers. And then you take an average, and you call that an index, basically. That's what this KP thing is. And what you find is that there's a seasonal dependence, too. Kind of amazing. But the geomagnetic activity spikes up at equinox, and it can occur any time, but it's more prevalent at those times. And for a long time, it was thought that was understood, something called the Russell-McFerrin effect. A couple of space scientists at UCLA proposed that effect, and now it's become more controversial, and even Bob McFerrin himself is not quite sure that that this is all due to the Russell-McFerrin effect. So it's an interesting control on geomagnetic activity. Let me move on now and talk a little bit about the impacts of space weather on humans and systems. How does it affect us? In other words, why do we care? It's interesting to see aurora, but why would you care about it? And there are quite a few different effects, and you can kind of see that this slide is a little bit dated. Bell Laboratories, Lucent Technologies. I don't even know if that place is around anymore. But it was developed by my colleague Lou Lanzarotti, and we, back in almost 20 years ago today, had made a pitch to the National Science Foundation, and they took and ran with it and got together a whole bunch of other agencies to advocate for development of a national space weather program, which exists today, and is really the body like the space, like the weather program, only for the National Space Weather Program. And so Lou put this slide together to help the people that we were trying to communicate the value of studying and developing forecast capabilities for space weather, why it would be important, and who would care about it. And military care, civilians care, and so on. So let me just start with some of the more obvious things. Astronauts, clearly, astronauts will tell you that they see flashes in their eyes when solar proton events occur. They tend to retreat into the interior sleeping areas to get a little bit more shielding from the protons, which are just going right through the skin of the shuttle, or we're not flying it anymore. Solar protons can affect satellite memory and upsets, so there's things called soft event upsets, which is an energetic particle going through a memory, electronic memory, and just causing a bit to flip. That's not a very damaging effect, but it does affect your control of the system, obviously. And then there are others where it actually materially destroys some of the electronics. Also, solar cell damage, satellite charging is an important issue for satellite operations. Through the ionosphere gets very disturbed, as John Ballard will tell you, and I'll say a little bit more about some of the things John Ballard has done. But it becomes very disturbed, and scintillations, so-called scintillations, occur in the ionosphere, which affect radio propagation through it. So scintillation, any of you have ever been in the desert or looking down a highway on a hot day, and you look in the horizon and you see that it's flickering. And the reason it's flickering is because the heat causes microturbulence in the air, and that changes the refractive index, and so the light that's coming toward your eye is bending along the way, and that's what gives the shimmer. Same thing happens with radio signals as it moves through the ionosphere. And so that affects communications to satellites from ground receivers. Galactic cosmic rays, it's a different kind of weather that has to do with things that are coming from outside our solar system, and it tends to be anti-correlated with solar activity. Magnetic attitude control is affected by events. So, for example, during very strong storms, the magnetic field, the magnetic cocoon surrounding Earth, can actually be so compressed that its direction no longer reflects the direction of the geomagnetic field, but it reflects the direction of the interplanetary magnetic field embedded in the solar wind. When that happens, if you have a magnetic torquer or a magnetic attitude sensor on your satellite, it's now sensing the wrong direction of the magnetic field. Okay? And then ionospheric currents, so electrical currents, and I'll show you some of the results that we've done here at Dartmouth, flow in the ionosphere. These electric currents can induce currents in the Earth, actually electric fields in the Earth, and those electric fields will drive currents up through power transmission lines, any long conductor, power transmission, pipelines, and so on. Airline passenger radiation, for most of us, it's not an issue. We don't fly polar routes enough, but for pregnant flight attendants or flight attendants or airline crews who fly those flights a lot, they actually wear radiation badges to determine what the radiation dosage is. And during very intense storms, they're told to move down in altitude so that, because there's shielding from the atmosphere to these energetic particles that come into the airplane. Airlines really would like to just go right over the pole. It's the shortest distance. When these events happen, it can cost them per flight up to $100,000 for extra fuel and so So the airlines care a lot about this, and it's not just about radiation, it's about the communication. The most reliable way, not the most reliable, the way to communicate at very high latitudes above 82 degrees is by high-frequency communications, and when the ionosphere becomes disturbed, it's very difficult to communicate with HF. Feel free to interrupt me. I really like this picture. This is about the future. I'm not going to say. I'm going to tease out 3 of those effects a bit more here, and I'm not going to say too much about this one. But if you look at this picture closely, I think you can see that this thing is moving. The discs in the back. See the dust being kicked up on the back. Look at the cab. There's nobody in it. It's being controlled by GPS is being used to guide it. And actually, in the agriculture business, this is a huge effect or utility because plowing the rows straighter actually improves yields. And so another application similar to this, grading roads, Caterpillar, for example, sells road graders that use GPS that say where it is horizontally and actually how far that blade is up off of the ground. And so they can get very precise road grading by using GPS now. Okay, now, if you think GPS is reliable and it's not because of scintillation phenomena in the ionosphere and you can't get the vertical distance right, but you think it is, you may not know what you're doing. So those folks would like to know more about when space weather is going to affect their operations. Surveying, oil drilling, sideways oil drilling are uses. Okay, so I'm taking you now to the NOAA Space Weather Prediction Center, and they're now running a model routinely called the WSA Enlil model. It was actually developed by the Center, Dusan Ostersill, who was associated with the Center for Space Weather Modeling that Joe mentioned earlier. And so what you're seeing here is a picture, this is the sun. And these are streams coming out from the sun. There's no storm. There's actually a storm that occurred 3 days ago, October 8th and 9th, late October 8th and 9th. There was a minor storm that came out that's not captured anymore because this timeline only goes back a day, and then it's tending to look outward to give some forecast capability. What you're seeing here is a picture out of the ecliptic plane. So this is what the structure looks like out of the ecliptic plane. This is in the ecliptic plane. This is Earth. And these 2 things here are the stereo satellites. So these are 2 NASA research satellites, stereo. And they were developed and launched to give a stereo view of what's coming off of the sun. When you're sitting at Earth, when you're sitting here, and something comes right at you, you're blinded. You can't see it coming. Once it gets off of the limb of the sun, and you can start to see it moving out, these are huge structures, you get a sense that there might be something coming. But if you could sit over here and look at something leaving the sun coming toward Earth, you have a chance of seeing what's happening. They're in the same orbit as Earth radially, but they're now on the backside of the sun, basically. But they'll come around again. Okay, so this is one of the tools that was developed to help, and it's basically a large-scale magneto-hydrodynamic, gas dynamic model that takes information at the surface of the sun and propagates it outward, beats it to Earth, basically, numerically. It's a numerical forecast model, in effect. It's good for large-scale structures, but for small-scale structures, it's not so good. Let me come back to the Carrington event. Thank you.
I just never heard of the term ecliptic plane.
So it's the plane in which the sun, the Earth, the planets are in the ecliptic plane in the solar system. So everything's orbiting in that. Okay. Massive CME misses Earth. Okay, so most times we would know nothing about such effects, but now we have stereo. And so stereo is sitting over here. Let me use the pointer. Stereo A and B, the red and blue dots are sitting here. Here's Earth, other planets and so on located. And this particular image from WSA Enlil was taken on July 24th, 2012, a little over a year ago at noon. And you can see this massive CME structure comes out. This plot here is the radial velocity moving outward from the sun, and this plot here is the relative density moving out from the sun. This is a coronagraph image from stereo showing the blowout of the structure coming out from the sun. And people took this event and they said they were able to take measurements at stereo, and they said, well, what if this had come to Earth? What would the impacts be? And the variations are anywhere from a storm. The Carrington event was about 1,700 nanotesla. This one was estimated to be somewhere around 450 to 1,200 nanotesla, given the uncertainties and so on. So whether these things impact Earth or even come to Earth, there's a lot of variability as to when they blow off of the sun, and then how intense they are when they do. NOAA keeps space weather scale for geomagnetic storms, and you can't possibly read all of this in the short time that we have here. But they go anywhere from minor to moderate, strong, severe, extreme. The Carrington event is an extreme event. And as I mentioned, the storm that occurred earlier this week was a minor to moderate event. And some of the simulated results that I'll show you are from events that are strong to severe. Okay. Let me talk a little bit about United Airlines polar routes, because it gives me a chance to talk a little bit about John Ballard. So what you see here are the polar routes that United Airlines uses to go from the United States to China, Hong Kong, and Shanghai. I think in one year they do something like 1,200 flights or something, an enormous number of flights. So whenever there's an event, and if it's $100,000 per flight effect, then they want to know about it, and they would like to be able to do something about it. And one of the problems, besides the radiation hazard, is that when you get in this circle at high latitudes, this yellow circle that you see on this chart here, HF radio communication is the main vehicle for communicating. And flights, pilots, air traffic control do not want planes in blackout for any period of time. They want to know where they are. If there's a collision, they get out of the way. If they're in trouble, where you're going down, all the things you can imagine why you would want to be in constant communication. And when HF radio goes out, they have to avoid that region and fly at lower latitudes because they don't have communication there. And one of the things that, in addition to storms which disturb the ionosphere, solar proton events, which usually are associated with geomagnetic storms, but not always, can significantly impact the high-latitude ionosphere. This is a plot of the flux of solar protons at energies of 16 to 35 mega-electron volts. And when those protons precipitate into the Earth's atmosphere, they change the state of the ionosphere. That affects high-frequency communications. Okay, so let me say a little bit about high-frequency communications and what some of the issues are here. So, very simple picture here. Different ways of communicating with an airplane. Line of sight. That's obviously one of the simplest ways to do it if you have a line of sight. If not, up to a satellite and then down. Space wave. If that's not available, then there's the Skywave. This is how traditional HF communications, bounce it off of the ionosphere and then receive it somewhere else. The Skywave. And then in a disturbed ionosphere, the Skywave does something like this. First of all, it can change where it's reflecting and coming back down. And then worse, because the ionosphere is lower in the atmosphere due to the solar proton precipitation and other things, the absorption of the radio wave occurs. And so it may not even reach with appropriate intensities where you want it. And so you have a situation like this. I'm going to, at the risk of oversimplifying something that John's done, but John and his colleague John Goodman figured out an ingenious way to actually sample what's going on in a disturbed condition in real time. So if you have two receivers sitting here and you're sending up radio waves, HF radio waves, at different places at different frequencies, in principle you can find out where there's a path that's going to be usable for communication with an airline. Dynacast, I think it's called. Is that right, John? Dynacast. And so it's an active system. It's nowcasting. It's not forecasting, but very useful for HF communications. In fact, so useful, I think RPSI, Radio Propagation Services Incorporated, has now been acquired by the Carlyle Group, I think. So anyway, it's obviously a lot of value there. And I like the analogy that John gives about reflecting radio waves off the ionosphere. It's kind of like sitting in a swimming pool and looking up and seeing waves and seeing all of the structure above you. And that's basically what it's like when you're sitting on the ground trying to look at the ionosphere with HF. Okay, another area of interest, solar storm risk to the North American electric grid. I mentioned that Hydro-Quebec went down. Basically, there are a couple of different factors that influence where the effects will occur. One is the ground conductivity. So if you have low conductivity ground, you can sustain a higher electric field at the surface of the Earth, and that electric field will drive currents through any conductors that are anchored in the Earth, that are grounded. Currents that you really hadn't anticipated were going to happen. And the other thing and then also if you're near the ocean, then the ocean, because it's conducting, particularly seawater, it's a pretty good conductor, it tends to shield the electric fields there and move them over toward the land. So the eastern seaboard of the United States kind of has that issue. And then there's this huge igneous rock formation in this part of North America that also has low conductivity. So the electric fields are induced by, it's like a transformer effect. From simple figure developed by Antti Pulkkinen, who runs the Coordinated Community Modeling Center at NASA, specifically looking into some of these effects. But basically, it's like a transformer. You have these electrical currents flowing on the ionosphere, and you have a conducting Earth. And so you know that when you have a current or a magnetic field that varies quickly, transformers are basically alternating current devices. And so when that current varies in time, it induces in the secondary winding an EMF and drives a current there. And that's basically what's happening between the ionosphere and the Earth in these effects. And so when that induced electric field develops on the surface of the Earth, then it can drive currents through long conductors. And actually pipelines have issues. Prediction's not such a big deal for them, but corrosion and so on is a huge factor, particularly at northern latitudes where these induced currents occur. And for the so-called Halloween storm, people who work in this field really like to name storms after the Bastille Day storm, the Halloween storm, and so on. So they have many very interesting names. And so there was a study done by a group at the USGS to try to get a sense for some very idealized magnetic fluctuations associated with the Halloween storm in 2003, what the geoelectric fields would look like over North America. And the thing what kind of struck me, notice that there are 3 minutes between these two plots. 3 minutes. Look how fast things are changing. I mean, that's how fast things change in space, and the effects show up on the ground. Okay, so if you're going to try to predict these things, you need to have a model that actually has a certain amount of fidelity in predicting some of the dynamics. And one of the things that we realized after going to some meetings, maybe 6 years ago, I think, was that there's this phenomenon that was observed in geospace, particularly on LANL satellites, Los Alamos satellites. They called them Sawtooth Events because of the way they look in the time series. So these satellites are in geostationary orbit, 6.6 RE out. And they're measuring energetic electrons and protons. And they have a whole bunch of them. They're not just one. Their job is to monitor radiation particles coming from detonations, for example, nuclear detonations. And so their detectors are pretty sensitive. And they saw this phenomenon, and they're like, what's going on here? And it's happening for 24 hours. These events, so these are different Lanel satellites, and you see these variations, orders of magnitude variations in the flux of these energetic particles on these satellites occurring over a period of 24 hours. And the interpretation was that this thing, going back to one of the first slides I showed, is that there's this periodic activation in the so-called magnetotail. And when that activation occurs, it's like a slingshot. Those field lines, magnetic field, is slung toward Earth, and it accelerates the particles, and that Lanel satellite's sitting there, and it's seeing it. Okay, that's sort of the interpretation that had been advocated, been seen for 20 years, and nobody really knew why it was happening. And we had this idea. I was talking to one of my grad students at the time, Oliver Bramble's now a research scientist and working for a startup company here locally, Norwich Technologies. And I said, Oliver, can we make a Sawtooth event in the simulations we're working with by hook or crook? Anyway, let's just see if we can make it. And then if we can make it happen, then we can see what we have to do to make it real as opposed to contrived. And Oliver took that challenge on. And so this is a simulation. What you see here is the Earth's magnetosphere, much more realistic. So solar wind coming from the left. The sun is over here to the south somewhere, probably down in Boston or D.C., way down there. The simulation has an inner radius of 2 Earth radii, so the Earth is inside here. And these white lines are the magnetic field out in space, and this is a time series of the interplanetary magnetic field, the component normal to the ecliptic plane, north-south to the ecliptic plane. That's BZ. And it's relatively steady. Okay, this is the event that I showed on the previous slide from the Los Alamos satellites. Relatively steady, and yet these sawtooth things are happening. Like, what's going on? So this is not the contrived one. This is one that we tried to do our best job. Oliver tried to do his best job and made a nice PhD thesis out of it. And what you see up here in this little panel up here is a model that we developed for the outflow of ions from the ionosphere. So basically, the effect is all of this activity happens in geospace. It sends all of this electromagnetic power down to the upper atmosphere and ionosphere. The ionosphere gets exercised and sends ions back out. Okay, and so that was an effect that we thought was important, and we're the first to test it. And so these numbers here indicate where the magnetotail. Basically, you can see when this red line goes near one of these, to the end they're kind of faint, and there's a different diagnostic. But when it comes back around, you can see that this is density plotted here, log ion density in the region around space, and this is the flux of the ions coming out from the ionosphere in the model. And you can see these things, kind of high-density regions that peel off and go down tail, and then the field lines, the magnetic field snaps and goes back earthward. So with an almost steady interplanetary magnetic field and steady driving, the system is still oscillating. It's like an internal oscillation, a relaxation oscillation. And it got quite a bit of attention from the research community. Science magazine accepted the paper for publication. And for the same event, just this morning, Oliver and Ben Zhang worked together to develop this figure to show you just how important the outflow is. So this is a picture of the horizontal current that flows in the ionosphere. Basically, you can think of it on the surface of the ionosphere practically. And the intensity of the current is color-coded, and the direction of the current is the arrows. And, of course, you take these currents, and you can determine what the geoelectric field is on the surface of the Earth from these kind of currents. No outflow with outflow. Huge difference. And so we think that we're getting these effects into these models to produce a more realistic result for use by operational forecast people at Space Weather Prediction Center, for example. Okay, another problem, and I'm going to try and go here pretty quickly. Orbital debris. Anybody here seen Gravity? I haven't seen it yet, but maybe this weekend. Okay. Okay, so this is a picture of the orbital debris in low Earth orbit. I took a note here to remind you. U.S. Space Surveillance Network has 25 sites across the globe. They track 16,000 objects continuously. Anything larger than a baseball in space. And when a geomagnetic storm occurs, you get these electric currents flowing in the ionosphere, electromagnetic power dumped into the upper atmosphere, the atmosphere expands upward. And that affects the drag on all of this stuff, and therefore where it is. They want to know where it is because they're trying to avoid collisions. A space station takes maneuvers occasionally to avoid collisions. Two satellites several years ago, a Russian satellite and one of the Iridium satellite. Iridium is the 66 satellite network of communication satellites, collided because nobody had their eye on the ball at the time. They could have maneuvered one of the Iridium satellites out of the way, but they kind of lost track of what was happening. And the Russians said, you know, we had no control over this satellite. It was dead. It's a dead satellite, but Iridium could have moved. And what happened? Well, now not only do you have two big objects in low Earth orbit, but now you've got a lot more after that collision, because these things are moving very fast speeds relative to each other. And the cloud keeps getting bigger. And actually, if you have any ideas about how to get this stuff out of low Earth orbit, it's probably $1 billion idea, I'm guessing, if not more. That they're proposing to use lasers, absolutely. To my knowledge, it hasn't worked yet, maybe because they haven't been able to afford it, but it's definitely one of the ideas that's out there. And of course, pardon me?
Use undergrads.
We just got to put some food out there, right? Right. This is what happens. Okay, so LEO is basically the region from up to about 1,000 kilometers altitude. The mass density down here, where we are in this room, is about a kilogram per cubic meter, and it falls off exponentially as you go up. But it's not zero up here. So while space is a pretty good vacuum, it's not a vacuum. And as the thermosphere, so-called thermosphere, expands upward, it affects the drag in this region. And what Ben Zhang, sort of contemporaneous with Oliver Brambles, did, he got interested in trying to understand how to use this large-scale model that simulated the magnetosphere. As John, it's almost every time I've seen John since we first met, will ask me, how is the magnetosphere? And so it's my opportunity to tell John how the magnetosphere is. So Ben got interested in trying to understand whether we could use that model to simulate the thermosphere and potentially the effects that it would have on drag. And there were these satellite anomalies. The CHAMP satellite's a satellite in low Earth orbit, 400 kilometers altitude. It's got accelerometers on it, and it calculates the drag effectively from the accelerometer changes in the drag, and it compared the thermospheric density that would be needed to produce that drag, and compared it to a standard reference model called the MSIS, and I forget what that stands for, but it's a reference atmospheric model. And they found these big anomalies in near noon at high latitude and pre-midnight, lower but still high latitude. And when Ben ran the model and used the NCAR thermosphere, ionosphere, general circulation model, coupled it into that, and included what he calls soft precipitation. These are electrons that are kind of in the range of 100 electron volts, with and without, found that, you get the same patterns if you compare the effects on the thermosphere with precipitation compared to without precipitation. So electron precipitation is the analog of rain here in the atmosphere. And so he's actually simulated a storm now with that knowledge, simulating a storm. So on the left is a plot of the thermospheric mass density in 10 to the minus 12th kilograms per cubic meter. And on the right is the precipitation of electron flux into the region. And this is a time series of the electric field taken upstream of the Earth's magnetosphere. This red thing gives you a sense of the direction and magnitude of the electric field, south being down to the ecliptic plane, basically. And the blue line is the magnetic field. But you can see that there is a huge effect from the electron precipitation on the state of the thermosphere and how much it upwells at 400 kilometers altitude, and therefore it's going to affect the drag on satellites there. And before Ben started doing this, there were some hints in the literature that soft electron precipitation may do such an effect, but nobody had ever studied it and actually quantified it. And that work was done here at the Thayer School by Ben Zhang. Okay, I said, I don't know, probably nobody here read the abstract of this presentation, this lecture, but I said I was going to talk about the practical, the exotic, and the sublime. This event here is the sublime. This is an event that's absolutely unpredictable. It might be, something like this might be coming at us right now, and we have no way of seeing it because it's coming at the speed of light from somewhere else in the galaxy or beyond. So in 2004, an incredible event occurred, and this was on the day side of the Earth. An object called a magnetar, SGR 1806-20, which was about 5 degrees off of the sun. This gamma ray burst came right at Earth from 50,000 light years away. Okay, that happened a long time ago. But it just got to Earth in 2004. And it lasted for about 6 minutes. Peak flux, for those of you in the audience who think about aurora, 20 milliwatts per square meter, will realize that's pretty big coming from 50,000 light years away. Aurora, an auroral arc that you would see in Alaska, will be produced by 10 milliwatts per square meter. Okay, so, but this is much more energetic. That's produced by electrons precipitating in the atmosphere, exciting atoms. These fluxes are due to gamma rays at very energetic, and it looks like I forgot to put the energy of the gamma rays on here, but very energetic gamma rays coming in. And they ionize the atmosphere down to 20 kilometers for an hour. John will really appreciate that number, I think. What you see here, if you look up, this is you're in the swimming pool and you're looking up at the nominal ionosphere right here. It's the black curve, this shaded region. And when these gamma rays came in, they moved, the ionosphere moved all the way down to 20 kilometers, and obviously that's going to significantly affect HF communications at those latitudes. So it is sublime in the sense that we can't predict it. It may be happening. We have no control over it. No point in getting worried about it. But we really are connected to the cosmos in ways that we can't anticipate. So these magnetars, they're basically collapsed suns, stars down to sizes of 10 kilometers, 50 kilometers. These are small suns that have collapsed. They've trapped this magnetic field because they're superconducting, and they rotate very fast and transfer some of that energy to particles. And most of the magnetars are in the galactic plane here. I'm not an astronomer. I'm sort of out of my element here, but this is where they occur. And we are told that there are no known magnetars closer than 9,000 light years away, but these are some of the most energetic objects we see. Well, let me just go quickly for the last couple of minutes and talk a little bit about the future. So one of the things that's going on here at the Thayer School that my colleague Simon Shepard has been developing is developing a what's called super dual array auroral radar network, phased array. And a couple of years ago, he and one of his students and colleagues at Virginia Tech built this facility in Christmas Valley, Oregon. They actually had the audacity at first to go to the Willamette Valley in Oregon and see if they could put it there. Now, I don't know how many wine aficionados we have here, but you can imagine nobody in the Willamette Valley is going to let something like this be built on their land. their nice pristine valley where they grow those nice grapes. Simon likes to say that this may be the largest experiment ever built at Dartmouth, 25-acre facility to take measurements. And so these are, John can appreciate the size of this thing. These are HF antennas. It's a phased array. And what a phased array means is that by controlling the phasing of the electric currents that are going into that antenna, you can point. You can choose the directionality of the signal that goes out. And to give you a sense of how this thing is used, these are actually all of the phased arrays in North America, or in the northern hemisphere. You can see there's a real paucity over the Russian sector. This one here should have been built, but will be built soon, Simon hopes. But the others all exist already. And they have overlapping beams, and this is what the array looks like in Antarctica in the southern hemisphere. And so I mentioned you can control the steering. So this is the look direction of one of the radars, and by phasing the elements, you can choose how it looks. You can do this with two of them, and there are more patterns that you can do. And when you do that, and you combine the backscatter, like you're speeding and the police measure the backscattered radar signal off of your car, well, you can do the same thing off of irregularities in the ionosphere. So shoot this beam up at the ionosphere and look at what comes back, and infer something about the motion. And so these kinds of maps are the analog of the precipitation wind maps that you see on weather.com, for example. This is where we're going with the capability to provide information about these systems. And I think I'll just go very quickly here. The NASA Heliophysics Division has actually a huge flotilla of satellites. Many of these, actually one of them was launched 50 years ago. Voyager. You probably read recently that Voyager pierced out. It's now outside the solar system. The solar system is basically where the intergalactic medium is pressing up against the the interstellar medium is pressing up against the interplanetary medium. And there's a sharp transition there. And Voyager went through it. But these are the satellites, including stereo and many others, that are being used today to gather information on space weather. So they're not all launched at once. They have a sort of a minimum lifetime. And then if their instruments continue to perform, they're given minimal resources to go to a minimum mission to continue to acquire data for what's called the Heliophysics System Observatory to provide information on sort of system-level behavior of what's going on in geospace and in the interplanetary medium. I think I'll skip this, and in the interest of time, it's 4:30. Just summarize and just say that space weather impacts many technological systems, and I only had a chance to talk about a few. If there's more interest in this area, you should invite my lovely and brilliant wife, Mary Hudson, who's a professor here in physics, to come tell you about radiation in space and how it's produced and so on. And she has a group that she works with in the physics department that studies that aspect of space weather. 100-year storms have widespread consequences. One of my slides, Lloyd's of London did a study. Lloyd's of London is required by the UK government to keep enough capital in reserve to cover the once in 250-year storm, whatever causes it. And so they're very concerned about whether another Carrington event would come and basically take down the electrical grid over Europe and North America. And the problem is that it's not necessarily a sort of like, oh, we'll get it back up in 3 days. When those systems fail, the transformers that fail are $10 million or more items. Those are not shelf items. They have to build those when they go out. And so the amount of time that it takes to get that part of the system back up could be devastating. And I don't know if any of you have lived without electricity for any number of days, but it's a sobering experience. Imagine 20 million people without electric power. It's really staggering. So there's been a lot of interest in these really extreme storms, but SWPC's job, Space Weather Prediction Center in Boulder, their job is really to monitor and forecast moderate storms. And that's what we're trying to do with the models we're developing here, with the radar systems that Simon is developing to facilitate better forecasts for your garden variety storms. And that's useful to spacecraft operators, power utility, communication system operators, airlines, so on. Our numerical forecast models are improving. Every year they get better, and someday we will have caught up with weather forecast models. The main weakness in getting advanced time, I showed you the picture that that NOAA SWIPSI uses, the WSA NLO model that takes information from the sun and propagates it out toward Earth. And they do a good job for these large-scale structures, but that handoff from that model to a geospace model doesn't work very well because they do not have enough small-scale information to give very much fidelity in the forecast that our models do. So when we run these models for events, we take data from a satellite upstream at L1, where basically think of the gravitational field of the Earth and the sun stand each other off, and you can basically park a satellite there, and you can measure what's coming, and we can use that to initialize the models and run them to get a sense of what they're going to do to the geospace environment. That doesn't give us much time. That gives us at most an hour from that point. That's how fast these things move. Okay. John, I wish Sue were here too. Thanks so much for giving me this opportunity to tell you how the magnetosphere is, and also for the chair. Very nice. I'd like to thank my wife, of course. Professor Banks Sunnerup, been really one of my heroes here at the Thayer School for a long time, and was instrumental in hiring and bringing Mary and me here in the 1980s. The seminar was really scheduled after he had already planned a trip to the International Space Science Institute. Banked is, I don't want to say anything about ages, but he's been emeritus for quite a few years. His pencil is still moving very fast. And so he's at the International Space Science Institute in Bern, Switzerland this week, working with a bunch of colleagues. And Simon Shepard, of course, my colleague here at the Thayer School. And then a whole host of others, students, former students, now research scientists, research associates who've worked with me, and my colleagues. We kind of loosely call ourselves the LFM, or Geospace Model Study Group, both here at Dartmouth. Actually, that large-scale model was first developed by John Lyon of the physics department, and we've been embellishing it in many ways to improve its fidelity here at the Thayer School. Slava Merkin at the Applied Physics Lab, Johns Hopkins, and Mike Wiltberger and Wenbin Wang at NCAR. Thank you.
And then there'll be a reception outside immediately afterwards where we can continue the conversation. I'll let you choose.
Yeah, I've been reading that the magnetic north is moving.
Yes.
And that it's accelerating up to maybe 70 or more miles in a year. I assume then all the effects we've talked about will move accordingly? Is that...
They will move. It hasn't moved that much. When I was a graduate student, the northern pole was 11 degrees off of the spin pole. You know, there's geographic north and magnetic north, and they differ by 11 degrees. I think that number is now around 9 degrees or something like that. So that kind of, I won't say when I was a graduate student, but it gives you a sense it's moving pretty fast. And a degree is maybe 110 kilometers or something like that. So it is moving. It's not necessarily monotonic. It kind of meanders. And then another thing is that the pole in the south, it's not like a magnet where they're on a line. The pole in the south is going off at some other direction. So it's not a huge deviation, but it is. But there have been geomagnetic reversals in geologic time. You can go back, and the Earth's magnetic field reverses, and that is before I think there was much life on Earth, if any. I don't know exactly when the last reversal was, but the consequences of that are enormous in terms of our magnetic field shields a lot of radiation from the sun and the galactic cosmic rays from getting down on the surface. When that field reverses, you know, it doesn't happen anymore. So, yeah. Yes?
What else would a Carrington event do today? Would it fry communication satellites, routers?
Well, the Halloween storm, actually, a Japanese remote sensing satellite looking down at the Earth failed. So the energetic particles that go into the electronics, this is a problem I like to assign one of my students in one of my classes. But when those particles lodge themselves in the electronics, and if that charge accumulates over time, sparks. And that can destroy the electronics and therefore the operation. So in some cases, it actually destroys it and they can't control the satellite. Satellite, you know, it's not a huge material damage, but it's enough to where if you can't communicate with it, you can't send it controls. You know, basically it's a dumb rock in space. And so that's one effect, and it's an important one, and there have been quite a few failures historically. I didn't talk very much about that here, but quite a few. You know, I think the main issue today is the power grid. That's got a lot of people worried. You've heard a lot about electromagnetic pulse, rogue nation detonating a nuclear device, and it has three effects. It has like high frequency noise that affects electronics. It sends out gamma rays, like that magnetar, and the low frequency end of that is like a solar storm, and at the same effect. And so, Lloyd's and study groups in the United States, James Woolsey, former director of the CIA, is part of one of those groups, trying to understand what we need to do to, you know, deal with either rogue nations or solar storms.
If there's a CME in a radial direction right towards the Earth, how do you detect that?
Well, you need stereo. That's one way to do it. If you have the two stereo satellites and you can look at it. But these CME structures are enormous. And so when they first lift off, you can't see them because you're staring into the sun. But eventually, they kind of go out, if you can imagine, almost conical shaped. They kind of come out from the sun. And when that ejecta gets beyond the limb of the sun so you're not blinded anymore, then you can start to see something and try to infer the directionality of it. But it's not easy, and that was the whole point of the stereo satellites was to get that stereo image.
One last question, Bill, was to get back to Keith.
Bill, I got a really important question. I want to ask you first, Ballard shareholder, and I think it's important that John's Keith Paulson asking this question because I think you'll really appreciate it. So if you as the shareholder get to rub John's head once a year for good luck. I've been trying this on my own head. It hasn't worked. Given all the success that John's had, the generosity shown Thayer, I think there's a good possibility. I urge you to put your
Okay, all right. Thank you.
I'm not sure I want to end on that.
I'm not getting invited to America.
But anyway, once again, thank you, John. Thank you to the Kittlesons for joining us, and thank you, Bill, and congratulations. Please, everyone, join us outside.
It's a lot of fun. I wish I would have had like another 2 weeks. I've really enjoyed sort of boning up on the literature and stuff, you know.
But that's always the case, isn't it? Right?
It's always-
Whenever the proposals do, whenever the proposal gets the deadline and say,
Yeah, if only, yeah. Right. So it turns out that my proposal that's due today, NASA decided that they're deferring it until the government opens. So I can submit it.
Can I take that from you, Bill?
I can submit it.